So sometimes we can have more than one Lewis structure. We saw that just recently. Let's draw O3. That's ozone. So ozone, we're going to have 3 oxygens. And we don't really have much choice but to just stick them in a line. Need the number of valence electrons. There's 3 of them. They each have 6 valence electrons. 3 times 6, I believe, is 18. So we'll start out by just putting a bond between these, because that's the minimum that we need. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Almost made it. These guys are happy. They both have 8. 2 on the top, 2 on the bottom, 2 on the left, 2 on the right. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6. Not happy, not okay. So I'm going to take a lone pair, a pair of electrons that's not already involved in a bond, from somebody else, and we're going to share both of those electrons in here. So I'm going to move these guys. And make that a bond. If this oxygen takes a lone pair and shares it with this other one, it still has an octet. It's not like it's really losing anything. Right? So now this one still has an octet, 2, 4, 6, 8. This one is 2, 4, 6, 8. And this one is 2, 4, 6, 8. Well, these oxygen atoms are the same element, but they're not the same atoms, right? If you think about a set of twins, identical twins, same DNA, but they're 2 different people, right? And they get really upset if you think they're interchangeable, because they're not. Well, these oxygens are like triplets. They're not interchangeable either. We could call this O1, O2, and O3, or give them silly names, but they're different. So why does this oxygen have the double bond instead of this one having the double bond? Well, we need to have an octet, so there has to be a double bond, but why does it have to be here? It doesn't. It doesn't have to be there. We can draw another perfectly good Lewis structure where we put that double bond on the other side.
When we draw the resonance or whatever, we're going to do the little brackets and do the arrows that go between them, right?
Yep. So we can draw these 2 Lewis structures. They look very much the same. But, if these were 3 individual people, they might argue about who got the double bond and who had the single bond.
Can we remove the one from the side and make it 2 double bonds, or no?
No, we can't, because if we take this and move it in here,
Right.
then the oxygen in the middle has 10, and that's not okay.
Okay.
Yeah. So in nature, the way this molecule actually exists is it's like an average of these 2 molecules. It's neither one or the other. So the Lewis structure can't handle this, Lewis model. And so what we do is we draw both of the structures, and that got a little messy. We draw a double-headed arrow in between them. And that double-headed arrow means that these are resonance structures. The true structure is like an average of them, but this is the best we can do. We can't really draw it. I think some people put brackets around it, but they're not necessary. Yeah. So those are called resonance structures. So it's important to understand that a resonance structure does not mean it's flipping back and forth, which is what the word resonance kind of suggests, right? It's resonating back and forth. They're just switching who has the double bond. No, it's more like a hybrid, right? So here we've got a German Shepherd and maybe a white lab, and these get together and have puppies, and so the puppy might look like this. The puppy has characteristics of the mom and the dad, right? But the puppy always looks the same. It's not, some days it looks like a German Shepherd, and other days it looks like a white lab, right? It's not how it works. It's a combination of the two things. These are the two resonance structures, but the true structure is a combination. It's a resonance hybrid, a combination of the two. And so here they've drawn a single line and a dashed line to try to represent a 1.5 bond. So in the Lewis model, electrons are localized, meaning they are around this atom or around that atom. But in nature, electrons can be delocalized. And that makes it more stable, and it's called resonance stabilization, and that's what's happening here. That pair of electrons is not between these two or between those two. It's delocalized over the whole molecule. Right, a Lewis structure for the NO2 minus ion include resonance structures. So here we've got nitrogen and oxygen. So I don't ever try to trick you on drawing the skeletons for these, because you could come up with a couple of different things, right? You could come up with something like this, or you could put nitrogen in the middle, right, and put an oxygen on each side. Usually things are going to be more symmetrical, and the other guideline is that you put the more electronegative element on the outside. So we look at nitrogen and oxygen. Oxygen's closer to fluorine. So oxygen we would predict to be on the outside, and nitrogen would be the central atom. Sometimes the question will specifically say, this is the central atom, and then you ignore that rule and you draw it the way they tell you to. So we're not going to use this one. Whoops. So here's our skeleton, and then we have to find out how many valence electrons. So we have 2 oxygens, they each have 6, and then we have 5 from the nitrogen. And then do we have an extra one, or did we lose one for the -1 charge? An extra. So that looks like 18 again. So we've got these single bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18. We don't have enough for everyone to have an octet with single bonds, and so we need to make multiple bonds. We're going to take a lone pair and move it to become a bonding pair. And then, because this is an ion, we need to put brackets and a charge on it. So if we don't include the charge, somebody's going to look at that and say, well, you got the wrong number of electrons. Could we draw this a different way? Yeah. When we see resonance structures, like 99% of the time, it's going to be where we have 2 of the same element, and one's getting a double bond and one's getting a single bond, or one's getting a triple and a single. We're just like, well, we could put that double bond on the other side, right? Why did it end up that way? Just because of how I happened to start drawing the dots is all that happened. So we can also draw it with the double bond on the other side. Put those guys too close together. And then to show that those are resonance structures, draw a double-headed arrow between them. Any questions? Okay, here it's asking us to recognize which of these is not a resonance structure of this one. So we need to look at these guys and see, well, what are the differences here? This one has triple and single bond. There's triple and single, triple and single. That one's got two doubles. But what else is different about one of these? Which element is in the middle? Here we have nitrogen in the middle, and all of the others have carbon in the middle and nitrogen on the end. The two or more resonance structures, you can draw them just by moving dots around. You don't have to reconnect the atoms in any way. So because this has the atoms connected in a different way, this is not a resonance structure of this guy. Because you'd have to break these bonds and totally rearrange everything. And resonance structure is just like, okay, we put the electrons here, we put the electrons here. So here we've got a single bond and a triple bond. You could also draw it like this, two doubles. Everybody's got 8. And we could also put the triple over here. So this one, there's 3 resonance structures. To choose between, like the one on the earlier slide where we had 2 different arrangements of the atoms, to choose between those sorts of differences, we use something called a formal charge. The formal charge is a little bit like oxidation state in that it's totally made up. So this is a fictitious charge assigned to each atom. And it's basically trying to keep track of, well, how are the electrons being shared and what's more fair, I guess you could say. So the formal charge is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. We do not need to consider electronegativity here, which makes it much, much simpler. So the book, of course, has to write out an equation and make it sound harder than it actually is. So if you like this, you can go ahead and do this. The formal charge for a given atom is the number of valence electrons that it has minus the number of bonding electrons and half the non-bonding the non-bonding electrons and half the bonding electrons. If you like that, awesome. I don't like that. I'll show you a different way in a minute. So formal charge rules, the sum of all the formal charges in a neutral molecule must be 0. So here this is kind of sounding like ionic charges or oxidation states, right? If the thing is neutral, it has to add up to 0. If it's an ion, these guys have to add up to the charge on the ion. Small or 0 formal charges are better. And if we have to have formal charges, we want to put negative formal charges on the more electronegative atom. Because that's basically saying, well, that atom has extra electrons in this molecule. And it's the most electronegative one that would do that. So we're going to look at two different skeletal structures for HCN. So structure A, we've got carbon in the middle. Structure B, we have nitrogen in the middle. So I'm going to draw them up here so they're a little bigger. And with this one, we're going to end up with a lone pair on the carbon and a lone pair on the nitrogen. I did the same thing. Nitrogen and carbon. Oops. Let's make these look as similar as possible. Okay. 2, 4, 6, 8, 2, 4, 6, 8, 2. So this is how you look at formal charges. So I think of this as maybe being like three people that went into business together. Hydrogen, carbon, and nitrogen. And then the money and resources that they brought to this business are their valence electrons, right? So hydrogen brought 1 valence electron, carbon brought 4, nitrogen brought 5. So they're business partners, and then things go south, and they're going to break up the business. So the way we're going to break up the business is we're just going to cut all the bonds in half. So we're going to cut that bond in half and cut the double bond in half. So cut this in half, and that each of these bonds is 2 electrons. That means that the electron on this end goes with the hydrogen, and the electron on the other end goes with the carbon. And so now what we're going to do is we're going to look at what do they have after the business dissolves, and did they lose or gain in this process? Well, hydrogen never loses or gains. It always comes out equal because hydrogen never has lone pairs, and it always has 1 bond. When that bond gets broken, hydrogen has the 1 electron that it came with. Hydrogen brought 1 electron. You cut everything up, it leaves with 1 electron. So its formal charge is 0. This carbon brings 4 valence electrons because it has 4 valence electrons, right? So we've got 4 valence electrons, and then we're going to count up what it's leaving with. It's got 1, 2, 3, 4, 5. It's got 5. So it started with 4, and it's leaving with 5, and that gives me -1. Okay, just shoot me now. Do you see what I did? This is what happens when you don't count your electrons.
Yeah, because I'm like, aren't the bonds too?
Yeah. I'll blame it on being old. I couldn't see the triple bond. I do it right now? Okay. Phew. Okay, we're still cutting the bonds in half. Looking at the carbon, it came with 4, and it's leaving. Don't do that to me. You're scaring me. And it's leaving with 1, 2, 3, 4. So 4 minus 4, 0. So that's the formal charge for carbon. Nitrogen brought 5 to the business, and when we break everything up in this molecule, it's leaving with 1, 2, 3, 4, 5. Leaves with 5, 0, broke even. Everybody broke even. That's a good thing. If we look at this one over here and break up this one, well, hydrogen always ends up being 0. But here's our nitrogen. Nitrogen brought 5 electrons to the business, and it's going to leave with 1, 2, 3, 4. So that's a positive 1 formal charge. The carbon here brought 4 electrons, and it's going to leave with 5. That's going to have a negative 1 formal charge. This is not as fair, because nitrogen is electron deficient and carbon is electron rich in this Lewis diagram. So this is not as good as this one. Any questions? This helps to start with the correct Lewis structure.
Where are the zeros negative for number of non-bonding?
Because you're subtracting something. So this is, the book saying, well, you've got number of valence electrons minus the number of non-bonding electrons, so minus 0, and minus half the number of the bonding electrons. It looks a lot more complicated to me. Let's just cut the bonds in half and see what they go home with, right? Compare to what they came with and call it good. So assign formal charges to each atom in the 3 resonance forms of N2O. N is central. Which resonance structure is likely to contribute most to the correct structure of N2O? So what we're doing is we're cutting the bonds, and we're going to see how they come out. So nitrogen came with 5. So this nitrogen came with 5, and it's going to leave with how many? 2, 4, 6. So negative 1. So this one's negative. I'll do it on the bottom. This one's negative 1. And the guy in the middle also came with 5, but he's leaving with 4. So that's plus 1. And oxygen on the end there brought 6 and is going to leave with 6. So that one's 0. This one's plus 1, and that one's 0. Let's do this one in the middle here. Nitrogen on the end brought 5 and is going to leave with 5. So this one's 0. Nitrogen in the middle brings 5, leaves with 4 plus 1. Oxygen brings 6 and leaves with 2, 4, 6, 7. Okay. And then let's look at this one. Now we've got the nitrogen on the left side came with 5, leaves with 7, so minus 2. Nitrogen in the middle comes with 5, leaves with 4, plus 1. And the oxygen on the end leaves with 5, so plus 1. So this one's minus 2, this one's plus 1, and this one is plus 1. This is a neutral molecule, and in each case, the numbers add up to the charge. I don't know what happened over here. Lower formal charges are better. Which one has higher formal charges, A, B, or C? C. We'd like them all to be 0, but apparently we can't have that, right? In A and B, at least one of them is 0, and the others are just 1s. Here, one of them is 2, and the other have 1s, and so this is not the best one. Now we can choose between these two guys. If there's a negative formal charge, we would like that to be on the more electronegative atom. So we've got nitrogens and oxygens. Who's more electronegative? Who's closer to fluorine? Oxygen. So this one, where the negative charge is on the oxygen, is going to be the more stable one. So this is our winner. Most likely to contribute the most to the correct structure. So here is an example where we see we've got multiple bonds, but they're not the same element on each side. So that can happen. And when that happens, then they're not exactly equal to each other, right? And so one might contribute more than the other. So I also say, like, our children are resonance hybrids of my husband and I, because all my ancestors came from Sweden and all of his ancestors came from Japan. But his genes had way more effect on what the children look like, right? People look at the kids and they're like, oh yeah, that's their dad. And then they look at me and like, who are you? Right? So he had more effect on them, and yet it's a combination, right? Any questions? Drawing resonance structures and assigning formal charges for organic compounds. So we're going to draw a Lewis structure, including resonance structures for diazomethane. So this is the formula, and they're telling us nitrogen is central. So we know we're going to put the nitrogen in the middle. The C is central, is carbon. We'll make it. We will make it. Okay. So carbon in the middle. And put the hydrogens around here and the nitrogens over here. We'll try that. We have 2 nitrogens, right? They each have 5 valence electrons. We have 1 carbon with 4 and 2 hydrogens with 1. So that's 10 plus 4 plus 2, 16 valence electrons. So we got 2, 4, 6, 8, 10, 12, 14, 16. Well, so that doesn't work out. We need to make double or triple bonds, which we should have expected, because in order to have resonance, there has to be at least a double bond somewhere. Can we take a pair of electrons from carbon to share with a nitrogen? Carbon doesn't have any lone pairs. And if we take a pair from nitrogen and share with carbon, then carbon's going to have too many, and nitrogen's still not going to have enough. So this is just not going to work at all, because it's the wrong skeletal structure. So let's try again. So the carbon's in the middle. Let's try putting the nitrogens and the hydrogens on the nitrogens. So 2, 4, 6, 8, 10, 12, 14, 16. Again, we run out. But now we can do something. So this nitrogen has an octet. It's got 2 lone pairs. The neighbor carbon does not have an octet, so nitrogen can be generous and share with its neighbor. It's like a preschool story or something. Sharing is caring. So there we got hydrogen, easily made happy. Here we got nitrogen, 2, 4, 6, 8. Carbon, 2, 4, 6, 8. But this nitrogen is not happy. So this carbon's going to step up and share its lone pair. Like that. Okay? So I'm just going to clean this up a little bit. So So that double bond's there. Is there another way we could distribute those double bonds? What if we had a triple bond and a single bond, and then we moved this lone pair over here? It's not working. Copy. Paste. There we go. So let's just do some moving around. So I'm going to move this lone pair over here, and I'm going to move move this guy over here. I just moved things. I just moved electrons. Still have the same number of electrons, still an octet, right? What else could we do? This nitrogen says, well, why do I only have a single bond? And that nitrogen gets a triple bond, right?
So that's something I would say.
Yeah. It's the sort of thing we all said when we were younger. And now that we're older, we just think it. You know better than to say it out loud, right? Okay, so those are the 3 resonance structures for that molecule. And it says assign formal charges to all the ones that have formal charges, which means if it's 0, we can skip it. So I want to show you a shortcut because you could say, well, drawing the lines and doing all the subtracting and stuff, that could take us a long time. Yeah, it could. So over here, I am just going to look at, let's do green. I'm just going to look at the Lewis structures for these elements. So there's hydrogen. Hydrogen has 1 valence electron. Carbon has 4 valence electrons. Nitrogen has 5. Oxygen has 6. And fluorine has 7. If you look at the Lewis structure for the element and you see, well, how many unpaired electrons does it have? That's the number of bonds it needs to make to have a 0 formal charge. Hydrogen has 1, it needs to make 1 bond. Carbon has 4, it needs to make 4 bonds. Nitrogen has 3 unpaired electrons, so it needs to make 3 bonds. So if we think of it this way, I can go over here and ask myself, well, how many bonds does nitrogen have? 1, 2, 3. Oh, well, that's what it likes. So this is going to have a 0 formal charge. And carbon, 1, 2, 3, 4, 0 formal charge. And this nitrogen, 1, 2, 3, is going to have a 0 formal charge. So this one has all 0 formal charges. If I go over to this one, here's this nitrogen has 1, 2, 3, 4. That's going to be non-zero. This carbon has 1, 2, 3, 4. That'll be 0. And this nitrogen has 2, also non-zero. So let's look at the ones that weren't 0 then. So for this guy, nitrogen has 5 valence electrons when it comes in, and if we cut these bonds in half, how many does it leave with? 4, right? So that's going to have a +1 formal charge. And this nitrogen over here brings 5 electrons to the business, and then we cut that in half, and how many does it leave with? 6. 2, 4, 6. So this one has a -1 formal charge, and the other one has a +1 formal charge. And if you don't believe me about all of this, let's do the carbon in the middle. Carbon has 4 valence electrons, and when it leaves, it has 1, 2, 3, 4. So having done this one, I can look at this and say, well, this nitrogen is in the same situation as that nitrogen. So this is going to have a -1 formal charge. This nitrogen here is like that one. It's got a triple and a single bond. So this is going to be +1. So which one of those is going to contribute the most to the resonance structure? Which one has the best formal charges? This one. These are all 0.